Hey, what's going on, guys? Today we'll be discussing the integration of natural policies into developing an LLM-powered policy gym for robotic manipulation. My name is Drew Shaw. I am a third semester VIP student in the Georgia Tech Vertically Integrated Projects Autobots team, and I'm looking forward to sharing what I've worked on with you guys. So let's take a quick recap on what I have worked on so far. My domain of work has primarily focused in the integration of large language models and robotic planning tasks. And I found that large language models show promise when generating semantically valid high-level plans for robot actions. I explored this through the generation of planning domain definition language models, where the robot kind of encapsulates a scene graph of information in a scene and can use that to prompt a planner for correct plan generation. However, I found that these planning domain definition languages are often just like syntactically created as like a file, right? It's like a specification. So when the large language model generates these PDDLs, there can be syntactic errors, excuse me. And so one way to kind of go about this is creating like a stochastic grammar correction engine where it goes through and kind of fixes up the errors to the best of its ability. Or the other way is to just use techniques like chain of thought or few shot prompting to improve the probability that you're going to get a correct PDDL model. And then finally, we looked at different medium constraints and different ways to serve the large language model. The language model can be run on CPUs through quantization, although not at such a high performance. It can also be run on GPUs on distributed architecture or local architecture. And then obviously you can use service providers such as OpenAI, Cohere, Anthropic, Google, or Microsoft. So based on some of this work I've done, I was like, all right, what's next? What's the goal this semester? So just a bit of a background for that. If you've kind of explored large language models at all, you kind of see that there's currently a large language model renaissance, or actually just a large model renaissance, right? There's new models being pumped out every week, or every day, even, or every hour, even. There's currently an uptick on new prompting techniques on model architectures, and then there's new modalities, right? Different ways to fine tune, lower rank adaptations, all those different things kind of play a huge part in the landscape that's being shaped today. So my goal is to create some sort of system, right, that allows us to experiment with all these different things that are changing like at a million miles per hour in a easy to interface with way, right? So how can we encapsulate all these changes and kind of test them on a robot as quick as possible, right? Though that's the goal of this project. So why LLMs, right? Let's get a bit of better understanding on why large language models are good for robotics in the first place. So large language models provide robots the ability to engage in intuitive and natural conversations with humans and take verbal instructions from users. This aligns better with human needs. Large language models also help robots understand natural language commands and execute various tasks like navigation, object manipulation, and specific actions. This expands possibilities for robot applications and is primarily the main focus of planning algorithms and the work I had done in the previous semesters. The flexibility of large language models enables robots to dynamically adapt to different tasks and environments based on their circumstances. This allows them to better meet diverse user needs. Through analyzing user feedback, large language models allow robots to continuously enhance performance and personalize services based on preferences. This improves human-robot collaboration over time. And finally, large language models support processing diverse inputs like speech, images, and text together. This multimodal capability allows more natural and rich human-robot interaction experiences, along with the fact that large language models possess powerful reasoning skills to break down complex instructions into executable steps. They can logically plan tasks and subtasks to accomplish goals based on the environment, leveraging knowledge and memory. This facilitates more intelligent robot-like behavior. And so much more, right? These are just some few ways large language models can be adapted modally to fit with robotics, but obviously, it's the possibilities are limitless. You're dealing with a not a non-deterministic system, so there's different various ways to use these interactive systems. So with new publications every day, we need ways to experiment rapidly. Thus, we introduce the goal of creating an easy to use platform that allows for testing easily and quickly through like using different LLMs, different prompting techniques, and stuff like that to see how it affects robotic planning and movement. This platform must be easily extensible by future students, right? So the overarching goal for this project is to create a system where students can just kind of come into, like, let's say the Autobots VIP, right? They can kind of come in and they can just take this software and kind of just go to work with it, right? They don't have to deal with setting up ROS. They don't have to deal with GPUs. They don't have to deal with infrastructure. They don't have to deal with like, oh, how am I going to get this model integrated? They can just kind of go and start building with the model, right? So of course, to enable this, we need to have some sort of simulation software so that has robust functionality. So we create a simulation or actually use some simulation software, right? I'll attribute it to the authors. So we'll use a simulation software that allows for robotic control planning whilst maintaining the functional primitives, right? And this must be, again, very rapid, easy, like kids in their second week of the VIP should be able to use this very easily. So we introduced PolicyBox. This is the software I developed this semester. It's a robust large language model robotics sim based on Google's robotics code as policies demo, right? So Google actually has explored this area and it's actually really quite impressive. So I was like, okay, let me kind of encapsulate this in a manner that allows for the utilization of large language models in a robotic setting and also easy parameterization, right? Google just provides a Colab notebook. It's not really very easy to parametrically change some of its factors, like the large language model that's been using, or the prompts, or the different structure of how the world is perceived, different things like that. So create some adapters for it. And it's a visualization based system, so you can kind of see the state of how the robot's moving around doing the whole simulation. And then the simulated physics is a gripper. It's a robotic arm, and this I will say this was provided by Google in their codex policies demos. I was able to adapt it for my use case. And then finally, something I actually developed for a personal project, but it ended up being really useful here is open source model service architecture. So it's a very easy Docker image to just kind of throw up on a provider like RunPod, GCP, AWS, or whatever, and you can kind of fire up whatever language model or whatever multimodal model you want on there, and it'll just kind of magically work through an OpenAI style interface. So, how it works. So, the software, obviously, I'll have a live demonstration as well. So the software can be prompted with examples to write robot policy code from commands. Policy code processes perception outputs and parameterizes the control APIs. So then the examples show mapping instructions to code using control flows and functions. And then hierarchical code generation improves performance by allowing undefined functions, right? So how the current architecture is working is we allow the large language model to generate some code for controlling the robot based on provided motion primitives. And then we execute that code to kind of run the robot, right? And experiments show that the method works across various robots and tasks. And we use a simulated tabletop environment. And this is kind of similar to imitation learning without needing domain training data, right? You can just tell it to go like, hey, pick up that block and put it in that bowl. And it's obviously very generalizable through the use of the large language model, right? You don't have to kind of encode every different perceptibility and possibility. You can kind of just let the model figure that out. And once again, yeah, the policies that the large language model create are just executable code through like different functions that I'll provide. And I can actually show you guys that once I have explained the language model adapter. So the language model adapter is something that I developed that allows you to have a unified interface to connect to open source LLMs. And the modified code base that I provide uses that, and the really cool thing about this is it uses the standard OpenAI specification format. So basically, you can just use the same endpoints you would use for like GPT or whatever, and just like make the exact same way, and it'll just work. And then it's hosted on RunPod or TensorDoc for cheap, efficient, performant testing, right? In my use cases, I think while I was using like a large language model for I think like 10 to 12 hours, it cost me like $1 at most to use. So it's very cheap and efficient, and you're getting access to really good computing power there. And I also have a custom load balancing scheme. This isn't really necessary for, let's say, a educational use case, but let's say, you had like you were doing a lot of different iterations of training. You just wanted to host the model on like some maybe some instance, and then for cost saving measures you wanted to terminate that instance, but you didn't want to like have to go through and like change the IP every time of the instance that you're using um, in your code. Then you can just use this tool to kind of just like dynamically reallocate to the new instance when it's booted up. So it's kind of cool. Let's go ahead and take a look at the software, and let's pause here for a little bit and take a look at the software. So this library will be provided in a GitHub link, and we kind of see that currently the entry point is just main.py and has a simple user interface that allows you to pretty much um, interact with the program. And then we have the large language model library, which obviously contains the interface for our remote server. Currently, we will just use the OpenAI specification because it performs the best, actually, as we found out. And then we have all these different things, like we have the language model program adapter, which is an adapter to kind of allow the robot to run code that the language model writes. And this is kind of what controllers, stuff like that, right? And then we provide a Docker file as well. So let's look at an example executional environment. So you kind of see the robotic arm here. This is a 30 by 30 image. It's currently zoomed out, but there's a robotic arm here, and sorry, 240 by 240 image, and this is going to be fully interactive, so the robotic arm can interact with this tabletop surface in a certain way. And so before we actually do the live demonstration, let me say, like, I told this robot, hey, put the blue box in the put the blue box in the blue bowl, right? And we can see that kind of does that. So let's go ahead and experiment with that. So you see here, putting the blue block. Sorry, I don't know why I was saying box. Block. Okay. Let's clear this, right? Let's get rid of these two images so we have that. And let's run this. All right, so let's look at our environment here. So this is our currently generated environment. So this is randomly generated. And these are the list of objects we have in this environment. So a task I see I want to do is I want to put the green block in the yellow bowl, right? So let's go ahead and tell it to do that. The green block in the yellow bowl. And this will kind of run. Now it does take a minute to run because it is obviously interfacing with the large language model, and we may even encounter some errors, right? So this is good to demonstrate if we do encounter errors, but in case we didn't, then it's good because the code generated by the large language model largely works. So current scene state saved too. So for after this, so this is the initial scene state. Obviously, every time you execute a command, you want to see the scene, kind of see like, hey, what happened in the scene? So this is kind of what the scene state looks like right now. And if we look at the thing, Boom. It places the green block in the yellow bowl. Now let's say I want to put the blue block on the green block. Let's see if it is able to. Oh, I forgot. Put it. Okay, it's able to infer. See, I forgot to put the letter, like the instruction put. So let's see if it is able to figure out kind of how to do that. Oh, and no errors. Awesome. Let's see. Does he say? Wow. Okay. So it does that. Boom. Awesome. Now I'm gonna try to. Do you see? This might not work. Remove all blocks from all bubbles. This might not work because. All right. So you can see here the kind of the policy it's generating. May not function correctly. But doesn't hurt to try. So it's doing something. Let's see here if it awesome. All right. So I guess that'll not work. So let's just end the execution there. But as you can see, that it kind of demonstrates the error-prone nature of large language models. And then finally, to wrap up the presentation, we will just discuss some results. So the instruct code models perform better than the chat models in this scenario, and the future steps involve creating a better interface, a more usable UI as compared to this command line UI, and then extensible modules, so like computer vision modules and different curriculum to help students develop with this software suite. So with that being said, I would love to share any information you guys would need for you to get this up and running. I have provided a virtual environment and requirements file for you to run the software. And it's actually kind of surprising that GPT-3 Instruct, Mistral 7b Instruct, and Code Llama all perform better than the GPT chat models, but obviously there is some freedom when the chat models kind of like interpret there. They have a higher temperature, and that may lead to some unexpected circumstances, but definitely open to further testing and suggestions, and look forward to seeing what you guys make with this. Thank you. Bye.